Okay, I think all is working. Okay, so now what we're going to do is basically what we did, when we went from Koshi's theorem to prove Koshi's integral formula, we took a very special function that had a removable singularity, which was the approximation of the derivative. We're just going to do this again, right? So we apply our theorem, right? Use our theorem, right? The one from removable singularities. To the theorem with this function, right? F of z equals f of z minus f of a over z minus a, right? And now this is a removable singularity, and will let us say something about the derivative, as we'll see. And this is the idea. We're just going to keep doing this over and over again. Okay, so let's make this a bit more precise. So f is an analytic in some region omega, a region. Okay, A is in omega. Okay, so now we take the function, right? So we take the function f of z equals to that, right? F of z minus f of a, z minus a, right? Clearly, f is analytic in omega without a, but the singularity around a is of course removable, right? It has the removable singularity at a, right? Because, we've done this a few times already, but let's do it again. Z goes to a, z minus a, f of z is, of course, just the limit of fz minus a, but because it's continuous, this is 0. Okay, so it has a removable singularity, so we can extend it to an analytic function, right? But actually, we even know what the limit is, right? Because in particular, f is continuous. The value of the extension at the singularity needs to be the limit of the function to that value, right? But actually, we do have a limit here, right? In the other case, we didn't quite know. We could have tried to define, right? Maybe think about this for a. Okay, let me write this, and then I'll try to give some intuition. So, right, clearly, by definition of derivative, right? This follows by the definition of derivative, right? And so it must be that when we extend the function big F, right, to this removable singularity A, this needs to be the value it takes, right? We don't actually need to go and do the Cauchy integral formula and compute any integrals, right? Because the resulting function needs to be continuous, so it needs to be this. Now I invite you to take a step back and think about what just, in the light of this, think about what just happened, right? We could have tried to define, we could have said, yeah, well, so let's take a function that's continuous, everywhere in a region except at a point. And now if the function has a limit value at that point, then I can extend the function to that point by just taking the value there to whatever the limit was, right? I could try to do something like this. Every time I have a function that's not defined at the point, then as long as it has a limit, right, I could try to define it to be that limit point and then hope that, being continuous wouldn't be so hard, but hope that it's still differentiable and try to prove things about it, right? But first of all, this seems hard to then try to argue that it's differentiable and so on. But moreover, we never actually, when our theorem about removable singularities, we never asked that f actually had a limit, right? We never required that fz to a of f of z actually had a limit. All we required is that it doesn't shoot up to infinity too much, right? Because we just require that this goes to 0. But if you think about continuous functions or forget complex analysis and analyticity, this going to 0 does not mean that this has a limit at all, right? And so something happened yet again with the power of smoothness over the complex numbers that just this, which feels like a much more, estimate type control, you just need to make sure that it doesn't shoot off to infinity, implies that a function is well behaved at a point, right? This is not true for functions in general. Okay, so I think as you follow, through this course, try to keep in mind how different, right, how strong this notion of smoothness is, and how some of the properties, as we prove them, we've sort of grown used to all these magical properties. But if you then go back and think about real functions, you realize some of these are really surprising. Okay, so we can define this object, right? And it's, of course, analytic by the theorem. Right, but if you were to just, without using Koshi integral formula, define this function, and then at a being this, try to argue that it's still differentiable, right? It's not clear at all, right? Okay. So let's define a function. This allows us to define f1 of z, right? In a function, let's say, from, again, the same region to C, such that f1 of z is equal to, right, will be fz minus f of a, z minus a, if z is not a, and f prime of a if z is a. All right, and this function is analytic. Right, we define sort of a linear approximation, if you will. But now we can just do it again, right? You just rinse and repeat, right? Right? Just repeat. Right? Now we can define, clearly we can use the exact same argument and define a function f2 going from omega to c, analytic, whose definition is given by, right, f2 of z is equal to f1 of z minus f1 of a over z minus a for if z is not a, and f1 prime of a if z is equal to a. Right, and of course, 2, 3, I can do this for any number. Really, what I have is a function, right, for any n, right, with f0 of z being f of z, right? I have a function fn of z, analytic in my region, right, which is defined to be f prime of a n minus 1 if z is a, right, and fn minus 1, z minus fn minus 1 a if z is different than a. Okay, so I'm just taking consecutive linear approximations. Okay, so in particular, I can now rewrite this in a slightly different way. Right? I can think of this, I'm defining the linear approximations, but I can write it in terms of the linear approximation it gives. Right? In particular, f of z, right here, is equal to what? Z minus a times f1z plus fa, so it's equal to f of a plus z minus a f1 of z, right? When z is not a, but when z is a is also true, right? Because when z is a, this term is 0, so it's of course also true, okay? And I can just keep defining these objects, right? f1 of z is just the same formula where I replace by f2, right? f1 of z is equal to f1 of a plus z minus a f2 of z, right? This is already getting the flavor of a Taylor approximation type of thing, Okay, and again, this holds when z is not a, but when z is a, this is 0, so it also holds. Okay, so in general, I have that f, say n minus 1 of z is equal to f n minus 1 of a plus z minus a f n of z, right? And in particular, all these functions are analytic. Okay, so now I have basically a Taylor series, right? Why? Because I have f of z equals f of a plus z minus a times this, but what is this? It's f1 of a plus z minus a times this, but what is this? Is then f2 of a and so on, right? So effectively, I have that f of z is f of a plus z minus a times f1 of a, which is like the derivative in the Taylor series, plus z minus a squared times this value at a, and so on and so forth, right? So effectively, I get a Taylor theorem, right, for free almost. I mean, for free. We've done a lot, but after we have this notion of removable singularity, it comes almost immediately. Theorem, let's call it, it's a version of Taylor. Maybe let me write it, a version of Taylor's theorem, because we're going to see other versions, right? So sometimes when we think of Taylor's theorem, we think of a power series, a certain radius of convergence. It's not quite featured yet here, but we're like almost there, but I don't want to quite do that yet, right? If f is analytic, right, in a region, then the following holds, right? F of z is equal to, okay, now we just use that formula over and over again. So f of a plus z minus a times, now the z minus a gets times this, but I get f1 of a maybe I shouldn't call this yet Taylor's theorem, because I'm still going to simplify this a little more. Okay, f1 of a plus z minus a f1 of a plus, now, right, there's this term, which is z minus a times z minus a is z minus a squared times whatever is in f2, but that's f2 of a plus z minus a of the rest, right? So z minus a square f2 of a, and I think you see how this is going, plus z minus a cube f3 of a, and so on and so forth, all the way to z minus a n times, right? I do this n times f of n of z. Now the important thing is where fn of z is analytic. Analytic in omega. Okay? The reason why, this is a theorem. The reason why I haven't called this yet, why I haven't yet called this the, I can do this for every n, of course. Right? We haven't called this Koshi's theorem is because it makes sense now to take derivatives, right? So now we want to determine what these f's are, just like how you do in Taylor series, right? So now we take n derivatives. Right? And so if we take n derivatives and set to a, and set z equals a, right? Just like how you do when you're doing Taylor series, then we get basically that, right, f nth derivative of a is equal to what? All these, right? All these terms cancel out, right? And so I get n factorial times fn of a. right? And so it means in particular that Fn of A is equal to 1 over n factorial of nth derivative at the point A. Okay, and so this now looks a lot more like Taylor's theorem. And that's what I'm going to call Taylor's theorem. Okay. Let's see. Let me erase here.
Excuse me?
Yeah?
In this expression for f of z, is the last thing the fn of a instead of fn of z? Last term in the sum? Above.
No, this is z.
Oh, no. Okay.
This is z, right? Because I haven't, this is the one where I don't close it out in the end.
Okay.
Yeah. Right? So I have f of z equals f of a plus z minus a f1 of z. But then I replace this with this one. Right? And I replace this with the next one and so on. But this fn of z I don't replace with anything. Right? I mean, in particular, f of z isn't really a polynomial, right? So it still has to have some freedom to not just be a polynomial in z, and this is where that freedom is. Yeah, but thanks. Okay. So now, okay, let me erase this too. Okay, maybe I should say, right? I took this derivative quite fast, right? But it's clear that the derivative terms, the terms up to here, they're a polynomial of degree n minus 1. So of course the derivative is 0, right? The derivative here, however, will have right. The f of n of z also has its own derivatives, right? And so there'll be terms, right? As we differentiate, we need to use the derivative of the product, right? But the only term, because I'm setting z to be a, the only term that survives and is not 0 is the one where this is differentiated exactly n times and this is differentiated 0 times, right? That's why the nth derivative of this expression after I set to a is just this value at a, right? If I wasn't to say, this formula is not true for any z, right? Because I get the sum of all the possible different ways of differentiating this. By possible ways, I mean whatever many times here and whatever many times there. But since I take z to be a, the only term that doesn't cancel out is the one where I differentiate n times here, right? That's why this formula holds, right? In particular, fn of z is not the nth derivative of f of z, right? It was given by these successive linear approximations. It's only true at the point a. Okay, so now I can write a theorem. Now a theorem, right, a finite version of Taylor. I mean, there'll be other Taylor theorems, but let me still call it Taylor. If f C is analytic, then for any n, for any integer, for any n integer, we have that f of z, right? We have a Taylor approximation, basically, right? Is f of a plus z minus a, right? I need to divide by 1 factorial, but that's times f1 of a Okay, plus a term that sort of is the residue in a way, z minus a to the n times fn of z. The important thing is fn of z is an analytic function. Now, I mean, you can imagine how now you can, prove all sorts of Taylor expansions with control over, right? You can think of your approximating f of z by an n minus 1 degree polynomial, say, right? And when you're very close to a, this thing is so tiny that as long as you can control that this doesn't blow up, you'll make sure that you're still close, right? So already with this, then you can get all sorts of quantitative things afterwards. Okay, so now what I want to do is I need some quantitative control on f of n, because I will want to show that basically I want to show that if a function, okay, let me see if I can give a bit of intuition, right? Maybe you remember these examples from real analysis in which functions are very, very smooth, but they're not analytic, the notion of analytic from real analysis, right? That all the derivatives are 0, yet the function is not identically 0, even in a neighborhood, right? And so, right, there's a few examples of this, and so they cannot have Taylor series and so on. Right here, this won't happen. This will never be the case, and I want to argue this. And so in particular, I want to argue that if a function, right, so the goal now, right, so we have this theorem. Now the goal of what we're going to show is argue that, so show that if f of a equals 0 and fn of a equals 0 for all n, then f must be 0. Must be identically 0, right? If all the derivatives are 0 around the point, then the function must be 0 in the whole region. Right? It must be 0 in the whole region. Okay, this is what we're going to do today, or the rest of today, because then this tells you will tell you very strong things. Let me see if I can both prove the estimates that will allow me to do this and the cool implications that it has. Now, we're going to have to do a bit of estimates, so like actual calculus. And I'll try to go as fast as I can over that, because I mean, conceptually, it's not really the main point. The main conceptual point is that this formula will allow us to get some control of f of n, and that control will allow us to then make this statement that is in blue, right? So this is what we're about to do. Okay. I saw there were some questions in the chat that it was close for me, but is everything clear? Oh yeah, I think this is what you asked on audio. Okay, all right. If anything's not clear, please just ask. So, okay. So now, how are we going to get estimates on this function? We're going to use Koshi's theorem on it, right? And it's going to be a little tedious to do, so I'll try to do it as fast as we can, right? So, like, let's do Koshi integral formula on f of n of z. Okay. Right. So of course, let's take. Let me define the objects. Let's take C circle around A with radius. So I'm going to need these numbers with radius r. And of course, the inside of C is in the region, right? Otherwise, it's a problem. Okay. Right, and the inside of C can be inside of a disk that's inside the region, right? Of course. And so, right, I mean, maybe I should just inside of C yeah, it's kind of clear. Okay, so you should think of C as inside a disk, as inside the region, right? I can always take a circle slightly smaller, right? So just so that Koshi theorem over the disk is more than enough. Okay. All right, so now let's write f of n is equal to, okay, now things are about to get a little tedious, I'm sorry. I'll try to just highlight the ideas without worrying too much about the calculations. Okay, so we have this, f of n, of course. Okay, but now we have the function, the formula for f of n, right? So now we're going to do this. Okay, so now let's write this. So this is equal to 1 over 2 pi I, integral over c. And now we're going to write a bunch of stuff here, right? So I'm going to grab this term can now be written in terms of all the other ones. All right, so let's first do it. I don't even know where to start. Right, so let's first have this one. So this will be what? F of z over then z minus a and maybe to make my life a little easier, let me divide here by c minus z. Okay. Yeah, that's a bit better. Okay, so now I just have to carry out all the other ones. Then minus, right, and I get f of a over z minus a to the n, then minus z, right, f, first derivative of a over 1 factorial, and then z minus a to the n minus 1, minus f2a over 2 factorial z minus a to the n minus 2, minus all of those, and then let me just collect the last one, which is the most interesting, which is what happens here. So this is f n minus 1 a, and then we have what? N minus 1 factorial, and then we have just 1 z minus a. Okay, all I did, it's quite tedious, was just, right, this equality, like equality sharp, I can now write fn of z with respect to the other things. Okay, so now let's collect interesting terms. So there is, this term is clearly special, right? Because it actually oh, did I just write z everywhere where I meant to write xi? Oh, okay. Yeah, okay. Yes. Let me look at it again. Yeah, of course, all of these are x's. Not this one. Yeah, that's changing the variables. Right, I'm swapping fn of xi, right? So all here. Okay, it's not so bad. Okay, not so bad. Okay. So clearly there's terms that are, this term is special because it actually depends on xi up here. These terms are a bit simpler. So we're going to separate into this term. Let's call it, 1 exclamation point. And these terms, let's call it double exclamation point. And now let me erase here, and basically you're going to show that the double exclamation points are all 0. Okay, first of all, I want to do this for z inside the circle, of course, right? Both a, let's remember, maybe it's a good point to remember, both a and z are inside C. Okay? It's a good thing to keep in mind. And oh yeah, someone asked about Xi. Yeah, thank you. Okay, so now all the other terms, so all terms, maybe let me use blue. Right, up to constants. Right, up to constant factors, which are like, right, things like f2 of a over 2 factorial, right? That doesn't depend on z or xi. Okay, they're basically all of the form integral of they're basically all of the form integral a xi minus a to some power, right? Let's say, right, to some power k times xi minus z. For k, right, going from 1 to n. K integer. Okay, so now again the goal is to show that these are all 0. Okay, let me define this object as a function. Do I want to make this a function of a? Yeah, I want to make this a function of a. Say fk of a to be this, right? And now the goal is to show that fk of a equals 0 for all k. Right, because if I get this, then I'm done. All those terms disappear, and I get the other estimate. Okay, so I'll try to do this very quickly. I need to clean this a bit more. Okay, so let's start with F1. What is it? I mean, there's a trick here. You probably can tell already what the trick is going to be. Okay, so we have something like this, right? But if we have something like this, you know, usually when we have fractions with different denominators, we make it the same. But here we can do it the other way, right? Because we can here do c minus a minus 1 over, no, xi. Oh, I keep swapping my x's and z, sorry. C minus z, right? If I have this, what is this equal to? This is equal to, you know, that, but on the numerator, I get xi minus z minus xi minus a, right? So I get a minus xi. So if I divide by a minus z, these two things are the same. Right? Take a second to see this. Right? If I now were to put this in the same denominator, I would get exactly that denominator. The numerator would be this minus this, That's exactly a minus z, right? The x's cancel, right? And so we know because, right? So what is this? This is equal to 1 over a minus z, basically, right? This is just by definition the number of times that c goes around a minus the number of times that c goes around z, right? But that's 0. We actually proved this directly, right? This is equal to 0 because, you know, the winding numbers of a and z are the same. They're both inside the circle, right? And now the observation is actually this is 0, right? This is equal to 0 for any a. For any a in the circle, right? In the inside of the circle. Right? Just not, you know, maybe not at z. Let's not worry about that. Right? And also it's not so hard to see, right? We saw that basically f of k, right, is essentially just a derivative, right? If you now apply that theorem that we proved, right, basically differentiating inside the integral to the function, to this function, right, that theorem that we had being this function, the function of xi, right, then when you differentiate this, what you get 2 over this squared, right? So when you differentiate the say, okay, f of 1, right, of a, right, what you get just 2, right, 2 times f2 of a. And in particular, you know, if I differentiate k times, I'm just going to get k factorial times fk of a. Yeah, right? And make sure I didn't swap the, yeah? And so this means that, you know, because that function was 0 for all a, then all of these need to be 0, right? So I know that these need to be 0 because the function was 0 everywhere, so are its derivatives, and so these are all equal to 0. Okay, so let me just say it again, because this was kind of a lot. f1 of a being 0 had a slick trick to it, but because it's 0 not just at the point a, but every time I vary, right? I can now vary a as much as I want, as long as I stay inside the circle. So all the derivatives need to be 0 too. And so we must have that f of k of a is 0 for all of them, right? So we got this. Good. Okay, so let me now erase, because I really want to show you the cool implication of this, and now I have only 7 minutes. So let me keep this. Let's take this is sort of the tedious part, but it's important to do these calculations. Okay, so what this means is that all the terms inside the double exclamation point are 0. Okay, so this is 0. And so we simply have that fn of z is equal to 1 over 2 pi I integral of f c over c minus a to the n c minus a to the n times c minus z. Okay, so this gives us a formula, right? A slightly different formula, but the formula for fn of z, right? Of course, for any z inside. Okay, so the reason why this is going to be useful is that, let's say, okay, let's take A now. Let's again, F is analytic, same conditions. Okay, let's take A in my domain such that F of A is 0 and the nth derivative of A is 0. Let me use K instead, because it's not necessarily the same. K of 0 for all k. Okay, the goal is to show that the function must be 0. If this is the case, then this means that for any, right, because of Taylor theorem, for any n bigger than 0, we must have that f of z, right? I expanded in the Taylor, but in the Taylor, the first few terms are all 0 because it's just the derivatives of f at a. So it must be that I can write this way. Right? And so I can always do this. For any n, I can write it. I can put a thing that should be very, very close to 0 next to a, right? Times something where f of n is analytic, right? Okay, but now let's take C, the circle, as before. Right, so a circle centered around A, right, in that. Okay, and let's say, right, F is nice and continuous. The circle is compact, so it must have a maximum. So let's say that the maximum over, the maximum of F, Z, for Z in the circle is smaller or equal than M, or equal to M, it doesn't matter. Okay. Right, and R is the radius. Now we use this formula, right? Now we use this formula to get an estimate. Right? Z is inside of C, and so now we do, I'm trying to debate if I should. Okay, 3 minutes. I think 3 minutes is okay. Okay, remember, R was the radius of the circle, and the circle is centered around A. No, some of these integral calculations are a bit tedious, but I promise the theorem I'm going to prove at the end is going to be worth the calculations. Okay, I'm setting up for it. Okay, take C as before this. Now what we get, Fn of Z. Okay, let me make sure that I just write the first time. Right, is smaller or equal than what? I'm going to do the same type of estimates I was doing before. So 1 over 2 pi. Right, now I get the size, the perimeter of the circle, so 2 pi r. Then there is an m that comes from here, right? And c minus a is always equal to r, so I get 1 over r to the n, right? And I get that term. Okay, but this term, right, z minus c, or c minus z, is always bigger or equal than r minus the distance between z and a, right? Just by triangle inequality, right? Draw a picture, right? I have a, I have z, this is r. The distance to the circle is always smaller or equal than the radius minus the distance to a, of course. So I can have a term here that looks like r minus z minus a. Okay. Okay, so now let's just simplify 2 pi, goes away with the 2 pi. I get an m. I get a r to the n minus 1. I get a 1 over r to the z minus a. Of course, again, z minus a is smaller than r. Okay, but now, so now I have this estimate, but what does this mean? Because I can write it that way, right? I have that f of z, absolute value, needs to be smaller or equal than z minus a to the n times the absolute value of f of n of z, right? I'm using this estimate plugged in here, okay? But what do I get if I do this? Okay, let's collect terms. So I get... So let's collect the terms to the n. So I have z minus a over r to the n. Here I had an r minus 1, so I need to put another r, another m, and another one of these. Okay. Okay, but now remember, z minus a was smaller than r. This needs to hold for every n, right? But if I take n, right, if I take n to go to infinity, right, then if I take n to go to infinity, z minus a over r to the n goes to 0. And because this needs to hold for all, right, because this needs to hold for all n, it must be that f of z is 0 inside the circle. Okay, so what we're showing, okay, so I need maybe 3 more minutes. Sorry for, otherwise I have to review this all next time. So I guess I'm 1 minute late. I need 2 more. So it means also that the derivatives, right? The derivatives of f, all the derivatives of f inside C are also 0, right? Because the function is 0. So if, okay, so if, r 0 at a for all n, then they're also in the neighborhood, right? Also true. In the neighborhood of A. So if I define the set E1 to be the set of Z's such that f of z is 0 and fn of z is 0 for all n, this set is open. Right? Because I just proved if it holds at a point, it holds at a neighborhood. Okay, but now let's define the set E2 to be the complement of this, right? The set of z's such that I'll just identify f0 of z with fz such that fn of z is different than 0 for some n. Okay, with the identification that f0 of z is just f of z. Okay, obviously this set is also open, right? Because if a function, they're all continuous, right? So if a continuous function is not 0 at a point, it's also not 0 at a neighborhood. It can't go from non-zero straight to 0, right? So this is so this is open as well, right? Because of continuity, like continuity of f of n z. And so because the region is connected, right, one of them must be empty. Okay, so it means in particular that either the functional derivatives aren't always 0, or it must have that, or it must be that if a function and all derivatives are 0 at a point, then the function must be 0 in the entire region. Okay? And so now, this might not seem super surprising, but what this means in particular Okay, so I'll do this again next week, right? So if you have to go ahead. But for those of you who want to stick around for 3 more minutes, I'll show you just very briefly and high level a very cool application of this statement, because we're basically right there. But I'll do it again on Friday. So if you have to leave, go ahead, of course, please. And sorry for already taking 5 more minutes. But I'm so close to a really cool theorem that I wanna show it. So let's say that I have. Okay, so let me erase here, and I'll do it again on Friday. Let's take some point z, right, in our domain. And let's say that f is not identically 0. Okay? Then it must be that one of those derivatives, there must exist some k such that fk of z, maybe I should have used the letter a, because that's the letter we've been using when we're fixing to look at local properties, right? Such that this is not 0, right? Otherwise, the function would be identically 0. Okay? But if this is the case, this means that I can write f of z as z minus a to this k times fk of z, such that this function, fk of z is not, fk of a is not 0. This means that, because fk of a is not 0 and this function is continuous, it's also not 0 in the neighborhood of a. So there exists a delta such that this is not 0 in the neighborhood of a, and because this is not 0 in the neighborhood of a except in a, then this is not 0 in the neighborhood of a, such that f of z is not 0 for z in the neighborhood of a, not in a. So what this means is that zeros are isolated. Now, this might again not look like much, but let me rephrase this in another way, right? This means that if you have a function whose 0 set has an accumulation point, right? It's not an isolated set, then it must be identically 0, right? And while this might yet not look super cool, what if I instead tell you that if I have two functions, like I apply this to the difference of two functions. So if I have two functions that agree on a set with an accumulation point, then the two functions must be the same.